A lithium-ion battery is a member of a family of rechargeable battery types in which lithium ions move from the negative electrode to the positive electrode during discharge and back when charging. Li-ion batteries use an intercalated lithium compound as one electrode material, compared to the metallic lithium used in a non-rechargeable lithium battery. The electrolyte, which allows for ionic movement, and the two electrodes are the constituent components of a lithium-ion battery cell. Lithium-ion batteries are common in consumer electronics. They are one of the most popular types of rechargeable batteries for portable electronics, with a high energy density, small memory effect, and only a slow loss of charge when not in use. Beyond consumer electronics, LIBs are also growing in popularity for military, battery electric vehicle and aerospace applications. For example, lithium-ion batteries are becoming a common replacement for the lead-acid batteries that have been used historically for golf carts and utility vehicles. Instead of heavy lead plates and acid electrolyte, the trend is to use lightweight lithium-ion battery packs that can provide the same voltage as lead-acid batteries, so no modification to the vehicle's drive system is required. Chemistry, performance, cost and safety characteristics vary across LIB types. Handheld electronics mostly use LIBs based on lithium cobalt oxide, which offers high energy density, but presents safety risks, especially when damaged. Lithium iron phosphate, lithium manganese oxide and lithium nickel manganese cobalt oxide offer lower energy density, but longer lives and inherent safety. Such batteries are widely used for electric tools, medical equipment and other roles. NMC in particular is a leading contender for automotive applications. Lithium nickel cobalt aluminum oxide and lithium titanate are specialty designs aimed at particular niche roles. The new lithium-sulfur batteries promise the highest performance-to-weight ratio. Lithium-ion batteries can be dangerous under some conditions and can pose a safety hazard since they contain, unlike other rechargeable batteries, a flammable electrolyte and are also kept pressurized. Because of this, the testing standards for these batteries are more stringent than those for acid electrolyte batteries, requiring both a broader range of test conditions and additional battery-specific tests. This is in response to reported accidents and failures, and there have been battery-related recalls by some companies. Terminology. Although the word battery is a common term to describe an electrochemical storage system, international industry standards differentiate between a cell and a battery. A cell is a basic electrochemical unit that contains the basic components, such as electrodes, separator, and electrolyte. In the case of lithium-ion cells, this is the single cylindrical, prismatic or pouch unit that provides an average potential difference at its terminals of 3.7 V for Liq2 and 3.3 V for LiFePO4. A battery, or battery pack, is a collection of cells or cell assemblies which are ready for use, as it contains an appropriate housing, electrical interconnections, and possibly electronics to control and protect the cells from failure. In this regard, the simplest battery is a single cell with perhaps a small electronic circuit for protection. In many cases, distinguishing between cell and battery is not important. However, this should be done when dealing with specific applications, for example, battery electric vehicles, where battery may indicate a high-voltage system of 400 V, and not a single cell. The term module is often used as an intermediate topology, with the understanding that a battery pack is made of modules, and modules are composed of individual cells. History. Before commercial introduction, lithium batteries were proposed by M.S. Whittingham, now at Binghamton University, while working for Exxon in the 1970s. Whittingham used titanium sulfide and lithium metal as the electrodes. However, this rechargeable lithium battery could never be made practical. Titanium disulfide was a poor choice, since it has to be synthesized under completely sealed conditions. This is extremely expensive. When exposed to air, titanium disulfide reacts to form hydrogen sulfide compounds, which have an unpleasant odor. For this, and other reasons, Exxon discontinued development of Whittingham's lithium-titanium disulfide battery. Batteries with metallic lithium electrodes presented safety issues. As lithium is a highly reactive element, it burns in normal atmospheric conditions because of the presence of water and oxygen. As a result, research moved to develop batteries where, instead of metallic lithium, only lithium compounds are present, being capable of accepting and releasing lithium ions. Reversible intercalation in graphite and intercalation into cathodic oxides was discovered in the 1970s by J. O. Besenhard at TU Munich. Besenhard proposed its application in lithium cells. Electrolyte decomposition and solvent co-intercalation into graphite were severe early drawbacks for battery life. 1973 Adam Heller proposes the lithium thionyl-chloride battery, still used in implanted medical devices and in defense systems where greater than a 20-year shelf life, high energy density, or extreme operating temperatures are encountered. 1977 Samer Basu demonstrated electrochemical intercalation of lithium in graphite at the University of Pennsylvania. This led to the development of a workable lithium intercalated graphite electrode at Bell Labs to provide an alternative to the lithium metal electrode battery. 1979 at Oxford University, England. John Goodenough and Koichi Mizushima demonstrated a rechargeable cell with voltage in the 4V range using lithium cobalt oxide as the positive electrode and lithium metal as the negative electrode. This innovation provided the positive electrode material that made batteries possible. Liku-2 is a stable positive electrode material which acts as a donor of lithium ions, which means that it can be used with a negative electrode material other than lithium metal. By enabling the use of stable and easy-to-handle negative electrode materials, Liku-2 opened a whole new range of possibilities for novel rechargeable battery systems. 1980 Rashid Yazami demonstrated the reversible electrochemical intercalation of lithium in graphite. The organic electrolytes available at the time were decomposed during charging with a graphite negative electrode, slowing the development of a rechargeable lithium graphite battery. Yazami used a solid electrolyte to demonstrate that lithium could be reversibly intercalated in graphite through an electrochemical mechanism. 1983 Michael M. Thackeray, Goodenough, and co-workers identified manganese spinel as a positive electrode material. Spinel showed great promise given its low-cost, good electronic and lithium-ion conductivity, and three-dimensional structure, which gives it good structural stability. Although pure manganese spinel fades with cycling, this can be overcome with chemical modification of the material. As of 2013, manganese spinel was used in commercial cells. 1985 Akira Yoshino assembled a prototype cell using carbonaceous material into which lithium ions could be inserted as one electrode, and lithium cobalt oxide, which is stable in air, as the other. By using materials without metallic lithium, safety was dramatically improved. Liku-2 enabled industrial-scale production and represents the birth of the current lithium-ion battery. 1989 Goodenough and Arumugam Mandaran of the University of Texas at Austin showed that positive electrodes containing polyanions, e.g., sulfates, produce higher voltages than oxides due to the induction effect of the polyanion. Commercial production. The performance and capacity of lithium-ion batteries increases as development progresses. 1991 Sony and Asahi Kasei released the first commercial lithium-ion battery. 1996 Goodenough, Akshaya Paddy and co-workers proposed lithium iron phosphate and other phosphorolivines as positive electrode materials. 2002. Yet Ming Chiang and his group at MIT showed a substantial improvement in the performance of lithium batteries by boosting the material's conductivity by doping it with aluminium, niobium and zirconium. The exact mechanism causing the increase became the subject of widespread debate. 2004. Chiang again increased performance by utilizing iron phosphate particles of less than 100 nanometers in diameter. This decreased particle density almost 100-fold, increased the positive electrode surface area and improved capacity and performance. Commercialization led to a rapid growth in the market for higher capacity LiBs, as well as a patent infringement battle between Chiang and Goodenough. 2011. Lithium-ion batteries accounted for 66% of all portable secondary battery sales in Japan. 2012. John Goodenough, Rashid Yazami and Akira Yoshino received the 2012 IEEE Medal for Environmental and Safety Technologies for developing the lithium-ion battery. 2013. A lithium rechargeable battery had progressed to a lithium vanadium phosphate battery to increase energy efficiency in the forward and reverse reaction. 2014. Commercial batteries from Amprius Corp. reached 650 watt-hours (L) using a silicon anode, and were being delivered to smartphone manufacturers. The National Academy of Engineering recognized John Goodenough, Yoshio Nishi, Rashid Yazami and Akira Yoshino for pioneering and leading the groundwork for today's lithium-ion battery construction. The three primary functional components of a lithium-ion battery are the positive and negative electrodes and electrolyte. Generally, the negative electrode of a conventional lithium-ion cell is made from carbon. The positive electrode is a metal oxide, and the electrolyte is a lithium salt in an organic solvent. The electrochemical roles of the electrodes reverse between anode and cathode, depending on the direction of current flow through the cell. The most commercially popular negative electrode is graphite. The positive electrode is generally one of three materials: a layered oxide, a polyanion or a spinel. The electrolyte is typically a mixture of organic carbonates such as ethylene carbonate or diethyl carbonate containing complexes of lithium ions. These non-aqueous electrolytes generally use non-coordinating anion salts such as lithium hexafluorophosphate, lithium hexafluorosinate monohydrate, lithium perchlorate, lithium tetrafluoroborate and lithium triflate. Depending on materials choices, the voltage, energy density, life and safety of a lithium-ion battery can change dramatically. Recently, novel architectures using nanotechnology have been employed to improve performance. Pure lithium is highly reactive. It reacts vigorously with water to form lithium hydroxide and hydrogen gas. Thus, a non-aqueous electrolyte is typically used, and a sealed container rigidly excludes moisture from the battery pack. Lithium-ion batteries are more expensive than NICD batteries but operate over a wider temperature range with higher energy densities. They require a protective circuit to limit peak voltage. For notebooks or laptops, lithium-ion cells are supplied as part of a battery pack with temperature sensors, voltage converter, regulator circuit, voltage tap, battery charge state monitor and the main connector. These components monitor the state of charge and current in and out of each cell, capacities of each individual cell, temperature of each cell and minimize the risk of short circuits. Shapes: Li-ion cells are available in various shapes, which can generally be divided into four groups: small cylindrical, large cylindrical, pouch, prismatic. Cells with a cylindrical shape are made in a characteristic Swiss roll manner, which means it is a single long sandwich of positive electrode, separator, negative electrode and separator rolled into a single spool. The main disadvantage of this method of construction is that the cell will have a higher series inductance. The absence of a case gives pouch cells the highest gravimetric energy density. However, for many practical applications they still require an external means of containment to prevent expansion when their stator charge level is high, and for general structural stability of the battery pack of which they are part. Since 2011, several research groups have announced demonstrations of lithium-ion flow batteries that suspend the cathode or anode material in an aqueous or organic solution. In 2014, Panasonic created the smallest Li-ion battery. It is pin-shaped. It has a diameter of 3.5 mm and a weight of 0.6 grams. Electrochemistry. The participants in the electrochemical reactions in a lithium-ion battery are the negative and positive electrodes, with the electrolyte providing the conductive medium for lithium ions to move between the electrodes. Both electrodes allow lithium ions to move in and out of their interiors. During insertion, ions move into the electrode. During the reverse process, extraction, ions move back out. When a lithium-ion-based cell is discharging, the positive lithium-ion moves from the negative electrode and enters the positive electrode. When the cell is charging, the reverse occurs. Useful work is performed when electrons flow through a closed external circuit. The following equations show one example of the chemistry, in units of moles, making it possible to use coefficient. The cathode half reaction is. The anode half reaction is. The overall reaction has its limits. Over-discharge supersaturates lithium cobalt oxide, leading to the production of lithium oxide, possibly by the following irreversible reaction. Overcharge up to 5.2 volts leads to the synthesis of cobalt oxide, as evidenced by X-ray diffraction. In a lithium-ion battery, the lithium ions are transported to and from the positive or negative electrodes by oxidizing the transition metal, cobalt. In Li-1X2 from Co3+ to Co4+ during charge, and reduced from Co4+ to Co3+ during discharge. The cobalt electrode reaction is only reversible for EX less than 0.5, limiting the depth of discharge allowable. This chemistry was used in the Li-ion cells developed by Sony in 1990. The cell's energy is equal to the voltage times the charge. Each gram of lithium represents Faraday's constant, 6.941 or 13,901 coulombs. At 3V, this gives 41.7 kilojoules per gram of lithium, or 11.6 kilowatt-hours per kilogram. This is a bit more than the heat of combustion of gasoline, but does not consider the other materials that go into a lithium battery and that make lithium batteries many times heavier per unit of energy. Electrolytes. The cell voltages given in the electrochemistry section are larger than the potential at which aqueous solutions will electrolyze. Liquid electrolytes in lithium-ion batteries consist of lithium salts, such as LiP6, LiBF4 or LiCl4 in an organic solvent, such as ethylene carbonate, dimethyl carbonate, and diethyl carbonate. A liquid electrolyte acts as a conductive pathway for the movement of cations passing from the positive to the negative electrodes during discharge. Typical conductivities of liquid electrolyte at room temperature are in the range of 10 millisiemens per centimeter, increasing by approximately 30 to 40% at 40 degrees Celsius and decreasing slightly at 0 degrees Celsius. The combination of linear and cyclic carbonates and dimethyl carbonate offers high conductivity and SEI forming ability. A mixture of a high ionic conductivity and low viscosity carbonate solvents is needed, because the two properties are mutually exclusive in a single material. Organic solvents easily decompose on the negative electrodes during charge. When appropriate, organic solvents are used as the electrolyte. The solvent decomposes on initial charging and forms a solid layer called the solid electrolyte interface, which is electrically insulating yet provides significant ionic conductivity. The interface prevents further decomposition of the electrolyte after the second charge. For example, ethylene carbonate is decomposed at a relatively high voltage, 0.7 V versus lithium, and forms a dense and stable interface. Composite electrolytes based on Po provide a relatively stable interface. It can be either solid and be applied in dry Li polymer cells, or liquid and be applied in regular Li-ion cells. Room temperature ionic liquids are another approach to limiting the flammability and volatility of organic electrolytes.